What do we call this 3? I mentioned it a couple times, but it's not something I've mentioned as much. Because this is what tells me it's a cube root, not a square root. Say it again. That's called the index. Okay. The reason why I want to encourage you on recognizing this is because it's going to help you, again, recognize the roots. And we're going to go into square root and cube root functions in the future. So I want y'all to think about this. I also want, everybody go grab a calculator real quick. Everybody needs a calculator in hand. Remember how to get to that cube root symbol? Go to a calculator page really quickly. So remember that cube root is above that caret symbol. You keep going. All right, give it a comment. Where you look. See, it says press menu, hit menu, and you're going to calculator page. So help each other type in that cube root of 25. Good. Tennis ball. I'll just put it on later. Okay. Yeah. Okay. Now I want you to type in the cube root of 25 squared and 25 to the 2/3. So not at the same time, two separate ones. So type in the cube root of 25 squared and 25 to raised to the 2/3. Okay. Same thing again. Cube root, so remember above the exponent symbol right there is that root. So you can control that, and so you can do any root now. Okay, so these are what? The same thing, okay? So the reason why I just want to point this out, I'm not going to assess you on this yet, but it's going to come back up later. And I just want to go ahead and tell you, like, this is an easier way to type things into the calculator a lot of times. So when you have a rational exponent, why am I calling this rational? Because it's a what? It's a ratio of integers, right? Remember that rational means a ratio of integers. What does the denominator in that rational exponent really mean? Think about what we saw up here. What does that denominator actually mean? The what? Close, but it's not a cube. Let's build on that. It's a cube something. It's a cube root. The denominator is telling me which root I have. That's it. What's the numerator telling me? So the exponent or the power, right? So how could I rewrite the 5th root of 4 to the 7th? Whoa. 5 divided by 7? Alright, so let's test that. Type in the 5th root of 4 to the 7th, and type in 4 to the 5/7. I don't know, let's test it. Okay, we got 2 options. I'm not sure, tell me, test it out. Which one is it? Did you actually check it? You just know it. Let's actually test it out. Landon, it helps when we test it out. There's one of them that is. Test it though. There's a difference between knowing and experiencing.
Not right. Not the same. Okay. No, it's 705.
It's 7 divided by 5, 7
Yes.
This is the correct one? Okay. One thing, just because of the way Landon said this, and I think this is important to recognize, there's 2 different schools of thought on how we know something. In the ancient Greek world, to know something meant to just intellectually be aware of it, to think about it. In the Middle Eastern school of thought, in the Jewish school of thought, to know something meant you had to experience it. And what I would encourage you, one of the reasons why I like us working on vertical surfaces is you're not just intellectually knowing something, you're experiencing the thing by talking about it, engaging in it. So engage in the process, experience it so that you can truly know it. If you're not actually experiencing it, I would argue that Middle Eastern, that Jewish culture or thought line of thought, to know means, or you have to experience to know, I think that that's very powerful. That's not something I learned until this past year, but when I heard that, I was like, this makes sense. To know, you have to experience. So take the time to experience it, not just intellectually know it. When you experience it, it becomes a part of you and it sticks long term. All right, so denominator, what is the denominator for that exponent? That's known as the what for that number? Look again. Is that a cube root?
Wait, no.
It is a root, but which root? I will say, I wasn't planning on talking about that, but which root is this?
I don't think so.
Well, I mean,
I don't think,
It's not a special word.
fifth root,
oh yeah, fifth root.
Okay,
Okay?
I just,
Like that cube root, we could just call it a third root, can't we?
but you got it.
So this would just be called a
fifth root.
fifth root, and then the 7 is the power, right? So it's the fifth root of 4 raised to the 7th. That's it. Don't make it more complicated. Okay? So you can call cube roots third roots. You can call square roots then what? Second roots, right? That's it. All right. Again,
Can we have Sadija call into the office, please?
she's on her way.
Thank you.
I'm not going to assess you on it, but that is going to be very helpful for you long term, so hold on to that. It also shows up on the AECT. All right, so remember we dived in yesterday to understanding these different number systems. Make sure you practice and you check with these. I apologize, I don't have a very model set of questions for this yet, because again, I've been crashing when I get home after playing with my son and just not having the time. Anyways, I'll fix that Monday to help you prepare for the unit or the 9 weeks exam. But we have to know the number systems. It's a matter of understanding what the thing is. Yeah. What I left yesterday with is I left you the charge of doing these. I gave you the answers to check yourself. Are there any of these that you worked through and you had a question about? Or are we good writing this with the number I in there? Say it again. Somebody's calling. Any questions about these four? Remember I gave you the answers so you can check yourself. Any questions about them? It's page 99. You have a question, Ken? Huh? Which one? D, as in dog? Okay, cool. All right. So one thing I want to remind you, let me ask y'all, I'm going to throw it to y'all. What could we do to get started on D? I'm not going to divide by 2 yet. Okay, so I need to do something with the square root, but like what?
I mean, like,
What do you mean by separate? Actually, so let me pause one thing, just because I thought about this. So Miles, one thing I want to point out is a square root, think about that kind of like parentheses in the sense that it groups stuff together. So what happens first? The grouping or division? The grouping, right? So a lot of students do like to do this, and those are not the same. Okay? You have to do the square root first because it's like a grouping symbol. It's a more powerful, is the way I describe it, than division. Okay? So, Sarah, you said rewrite it or separate it. What do you mean? Okay? So, Kenny, we'll build on that, this idea of separating it. Okay, so were you thinking about 6 divided by 2 minus the square root of 8, square root of negative 8 divided by 2, or are you thinking about separating something else?
Separating the square root by negative 8.
So separating the negative 8. Ooh, there's another word for separate there.
I don't know.
Does anyone know another word? We don't want to just move stuff. As soon as we get to this word, it's going to make a lot more sense what she's talking about.
Distribute.
What do we mean by distribute? When you distribute, what operation are you using? If I distribute, what operation am I using? Multiplication.
Yeah.
Am I multiplying inside of here? Is there anything being multiplied? So 4 and 2, okay, we're getting closer. Getting closer. So first things first, what is Landon talking about when he says 4 and 2? What's he doing there? He's separating it into what? Say it louder, Jaden. Factors. Right? Separate, factor. Notice as soon as we get to that language of factor, that is a type of separating, but that term factor more clearly says what we're actually doing, right? We're factoring it. Now I'm missing something. Miles? But I still have a negative, right? So how am I going to do that? A -1. Remember, we want a -1, because what's the square root of -1? So we always need a -1 as one of my factors. I always need that -1 as one of my factors. Notice what's 4 times 2? 8 times -1 is? So have I changed that number?
No.
Just rewritten it, okay? So how do I rewrite it from here? Closer. No, you were closer a second ago. Y'all are skipping like a really important thing in this thing. Hey guys, where does that square root go? Does it just disappear?
No.
No. It's not 4 times 2. Square root of 4.
Times the square root of 2. Times the
Oh.
square root of negative
Guys, the whole point is that I can separate into these individual radicals. So this is actually why I showed that idea earlier. So I promise what I'm about to do is going to connect. So we're going to come back to this in a second. 3 times 2 squared. Did you know that I can rewrite this as 3 squared times 2 squared? Because that's literally just 3 times 2 times 3 times 2. Right? So 3 squared times 2 squared. See how I'm almost distributing that exponent? And it's actually not almost. It actually is distributing. It's a different type of distribution. Don't stress about it too much. But because of this, if I have 4 times 2 times -1 raised to the 1/2, what does that 1/2 mean? Like connect it over to here. What's that 1/2 mean? It's what? No, I'm trying to say like connect that 1/2 to this. What does the 2 indicate? A square root. Well, square root, right? What do we have right here? A square root, right? So this square root and this square root are telling the same story. So my point is, I can distribute this exponent. So guess what I can do with this exponent? Distribute. So what I have is the square root of 4 times the square root of 2 times the square root of -1. My point is, if I can factor that radicand, I can split that one radical into how many radicals? 3 of them, right? For each root, right? Each factor has its own root. That's why this happens. So, we need to make sure we make a note about this because I I know we don't have Frere models to refer back to, but I clearly talked about this. It's in the book there. Factor the radicand and split the one radical into how many radicals? Into how many radicals? In this case, it's 3.
Right.
As many as you can, so as many what? Factors as there are. Now, one thing I will caution you is, it only makes sense to split it into a perfect square. Can I take the square root of 5? No, but can I take the square root of 25? So you're going to want to factor that radical into perfect squares and non-perfect squares. That's why I did 4 and 2. Okay. So now we take the square root of what we can, and we leave what we can't as is. What is the square root? Can I take the square root of 4? Yes, what is that? 2. Can I take the square root of 2? It's a decimal, not just a decimal, it's what type of number? Irrational, so do I want to write that out? No, so I leave it as the square root of 2. Can I take the square root of negative 1? I say, so I just rewrite it as I all divided by 2. Now I can separate it, as someone was mentioning, and I distribute that division. 6 divided by 2 is 3. Well, I'll try to rewrite it instead of. So 3 minus root 2i. Make sure that I is not under the radical. So again, this right here was just to illustrate why I can split into those radicals. But you split the radical into as many factors as you have. Make sure that you do every perfect square you can. What are your questions?
Why is I not in the
Because that is on its own. Is that underneath the radical here?
No.
So it's not under the radical of 2, and it's because square root of negative 1 on its own is I.
Okay.
Right? Remember, we've defined it so that I squared is negative 1, so I is square root of negative 1. So that I on its own already has the square root. We don't put it underneath the radical there.
Okay.
Good question. When you divide it, like you divide it here,
Oh, yeah.
so you actually made 2 mistakes to get there. So you did 6 divided by 2 minus, and you did 8 divided by 2. Yeah, that's the same thing as minus, right? And so you did 3 minus 4, or maybe plus negative 4. Either way, what you ended up doing is you then took the square root of that, but you took the square root of 4 and left it as the square root of 2. But square root of 4 and square root of 2 are not the same. What would the square root of 4 be? 2i. That's what you should have gotten. So you made 2 mistakes to get to the correct answer. So yeah, good question. Yeah, I love it. Good. Thank you for noticing that. I'll come bring the Starburst so you can grab Starburst, whatever one you want. Same thing. But good questions. So. All right, moving from there. And I gotta find out remote is bugging me. All right. Hope no one in Ford block stole it. That'd be rude. Okay, so moving in here. So we're on 6.3 on adding, subtracting, and multiplying complex numbers. So we have the complex number 2 plus 3i. And what we should notice is page 100, by the way. Okay? What does this look a whole lot like right here? Looks like a graph, right? It looks like a Cartesian coordinate system. I don't know if you've actually heard that term before. It's called Cartesian, based on René Descartes. He's the one that really kind of like pioneered the use of the Cartesian coordinate system, this kind of graphing notation. However, the Cartesian coordinate system has real numbers on the x-axis, and any guesses what the Cartesian coordinate system has on the y-axis?
Oh, imaginary.
No, so remember this looks like the Cartesian. What you've always dealt with is the Cartesian. Have you had imaginary numbers before? No? So you had real and you had, let's say,
Real and real?
we had real and real.
Oh.
Yep. 1, 2, 3, 1, 2, 3, right? Y'all are used to a system that had real by real. Well, now we have something that's not Cartesian. We have known as the complex plane. Why is it complex? It's got imaginary on the y, right? Like complex means we got real and we got imaginary. So why in the world is 2 plus 3i right here? Why?
2 and then 3 just right there.
Oh, so you went 2 in the which direction?
Right?
2 to the right because what's the x-axis? That's my
Real.
real. And then we went
3 up.
3 up for 3i. So what does 2 plus 3i remind us of that we have already studied? Well, it could connect to slope. I was thinking something even more basic than that. And that's the idea of slope. I was thinking something more basic. It's just a point, isn't it? It's a coordinate point. The x and the y, that's it. All right? So I want y'all to take 5 minutes. Because you need a coordinate system and I don't have those around the room, work with your group on graphing A through I at your surfaces. We will talk about this in about 5 minutes. Mr. Hobby and I will come around if you have questions. This page. And so Kelly was asking the question, hey, can we just add that 5 and that 5 together? What do y'all think? Yes?
No,
Who said no? Elizabeth, why not?
because you have to multiply the other 5, right?
So one, remember multiplication happens first, doesn't it? And so when I look at this, what I would think about is this is the number 5 plus root 2i plus root 2i, how many times? 5 times, right? So can I add those together? Can I add those root 2i's to that 5? So there's 2 reasons why not. One, even if it was just 5 plus 5 root 2, this means I'm adding square root of 2 how many times? 5 times. Do I have square root of 2 here?
It ain't gonna make sense.
It's not gonna go together. On top of that, I talked about this yesterday. What part of the complex number is this? Does anyone remember what I called it? Okay, what part of the complex number is this? There's a key letter up there that tells you exactly which part it is.
Imaginary?
Say it again.
Imaginary.
It's imaginary, right? What part is this?
Real?
Real. You think I can put real and imaginary together? Nope. I can't add those. So that's an excellent question. But do note, right, one, that multiplication, right, indicates that I'm repeatedly adding the square root of 2. The square root of 2i, technically. And so I wouldn't even be able to add it if it was like this. If this was 5 root 2 plus 5 root 2, could I add those together now? This literally indicates, just like 5x and plus 5x, this indicates I'm adding root 2 how many times? 5 times. Plus another how many root 2's? 5. So how many root 2's do I have? 10 root 2's. Does that make sense when we can and cannot add those terms together? We good with that? So don't forget also real and imaginary. Real can go with real, imaginary can go with imaginary. Comfy with that idea? Okay. So sorry, get back to graphing. We'll talk about these in just a second. Anybody have an idea how,
And then,
like what I could do
Yeah,
on
so it
G
would
to
be
help
just
me
like the
get
point.
started?
The square root of -1.
any starting point on G? Can I add 5 and 3? Well, let me ask you this, what's happening between the 3 and the square root?
Multiply.
Wait, which one are you talking about?
It's odd plus 3.
And it's multiply.
Oh, it's multiple. Maybe the same as the other ones? Oh.
Can I add those together?
Yeah. so
Say that again, Miles? What do you say?
I was saying, you can't add imaginary and real.
Wait, where did you get imaginary from?
What part were you on?
G?
I was talking about H.
Oh, okay. Let's look at G though.
Okay.
I want you all to build on square root of negative 1. What is that?
Oh, it's 3i.
Oh yeah. Hey guys, isn't that just 5 plus 3i? I need to remind you and I need you to not forget, if you see the square root of a negative 1, what should be your immediate thought? I. There's no question about that. Like when I see that square root of negative 1, my immediate thought is I. I rewrite it. So, same thing that I've always done. I went to the right 5 and up 3. 5 plus 3i. So check H and I from there. Do I still need to talk about those? What?
Make it an I.
Say it louder.
Say the same thing, make it an I.
Same thing, make it an I. Right? So check your points. Do you get the same H and I that I do? Okay, let me ask you this then. I want us to look at H. Why did I not go to the left 3 and up 3? Notice that's not where I have H. Why did I not go to the left 3 then up 3?
Real numbers positive.
So I'm looking at the negative 3 is first, so it's to the left 3.
No.
Oh, the x-axis is only the real. The y-axis is only the imaginary. Usually, you always write real first, then imaginary. So when I write like that, it's more clear that it's 3 to the right and 3 down. That's it. 3 to the right and 3 down. So real, then imaginary. If you ever look at anyone, any mathematician, anybody writes a complex number, it's always a plus bi. The real part first, then the imaginary part. What questions do you have about GH and I? Crushing it. Go for it, Shadidra. I mean, this one? Well, because that's what was already there. Negative 3, square root negative 1 plus 3. I first rewrote that as negative 3i plus 3, but notice I literally then rewrote it as 3 minus 3i. It's a positive 3, that's my real, and then the imaginary is a negative 3, so positive 3 minus 3i. Does that make sense? Okay. So real then imaginary. So I rewrote it there eventually. All right. I'm trying to think through for the sake of time. Here's what I want us to do. Is instead of thinking about it graphically first, I just want you to think logically based on what you know. I want you to add these two numbers together. And then together we will look at it graphically. In 60 seconds, try adding those two numbers together. 2 plus 3i plus negative 5 plus I. Try just adding those two numbers together. Don't pick up that calculator. Negative 5 plus I will equal.
Negative 3, 4i.
Why are we thinking that? Like terms, right? Let's think about that even more clearly with the concept of these complex numbers. What are going to be the like terms?
Real numbers and
Let's use better language than that.
Oh, real numbers and
Oh, the real numbers go together,
imaginary.
and then the imaginary numbers go together. That's it.
Are you smart?
Okay, that's it. So notice that's 2 plus negative 5. And like, if you think about it here, literally this means I'm adding I how many times? 3 times. And then I'm adding one more I, correct?
Yep.
So how many I's do I have? 4 of them. That's it. Now, what they're doing graphically here, I want you to see, is they're starting at the number 2 plus 3i, and to add a negative 5, what direction are they going? So to the left. Think about your number line, right? Isn't left negative and right positive? Has that changed?
Can we have Malia Joseph check it out?
She's on her way. And so then it's plus 1i, so it's going to go up one more. And notice, what are those coordinates? It's to the left 3 total. And how far up? 4. This idea of the complex numbers, I know it's like, oh, imaginary, they don't actually exist, but they do. This concept of a complex number perfectly ties into something called vectors that we study in physics and in higher level mathematics. And all a vector is this. Vectors. So in pre-calculus, vectors are a huge deal. As vectors, no. Complex numbers, yes. Right? So when I say a vector, though, it just means I have a starting point and I have an ending point, so there's distance there, right? See how there's some kind of, so like if I start from the origin, there's some kind of distance to that point, correct? Right, so from the origin to here, there's a distance, there's also a direction. That's all a vector is, a distance and direction. And so when we use these imaginary numbers or the complex numbers, it helps us understand vectors better and work with certain components of vectors better. So, again, I'm not assessing you on it, but just be aware that that's where you would be going with these complex numbers very heavily. That's why complex numbers are super useful. And you can convert to a thing called polar coordinates and all those different fun details. All right. So Kimani here, to add 2 complex numbers, you can add their real parts separately, then add the imaginary parts separately, and then combine the results into the form A plus BI. Is that true?
Yes.
Yeah, real go with real, imaginary with imaginary. I don't think we need to make that much more complicated. Is that fair?
Yep.
All right, moving forward. Now, I want you to, on number 5, is negative 3 plus 4i minus a negative 5 plus I equal to 2 plus 3i. Use the complex plane to confirm your answer. What do you think? Why yes? Does anyone know where negative 3 plus 4i is?
Huh?
Anyone know where negative 3 plus 4i is? That's where we're starting at number 5.
Yes.
Where is it? It was literally where we just started, wasn't it? Or where we just ended. So no, that is where we just ended in the previous problem, negative 3 plus 4i. And what are we doing to that negative 3 plus 4i? We're subtracting that negative 5 plus I. Now I want you to think about this. I need y'all to pay attention. When we added a negative 5 plus I, that meant we went to the left and then up. But if we're going to subtract a negative 5 plus I, what is that going to do? So we're going to have to move the opposite, right? So we're going to move to the right. How far am I moving to the right? 5. And then,
Oh, now?
and then notice it's again the opposite, right? So it's down 1. Same exact spot, right? Negative 3 plus 4i minus a negative 5 plus I is equal to 2 plus 3i. And so we can graphically see that. And so I want to point this out. There's a couple of things to pull from this. First, can I distribute here? Can you distribute with imaginary numbers? That'd be plus 5, right? So that'd be to the right 5, and it'd be minus I, that'd be down 1. So can you distribute with imaginary numbers? 100%. I would pay attention to that we can just distribute, again, add reals, add imaginaries. Now, the other thing I want to point out is this. Earlier, we had 2 plus 3i. We added negative 5 plus I, and that equaled negative 3 plus 4I. How can I take this equation and go to this equation up here? Because that is an equation, right? Negative 3 plus 4I minus the negative 5 plus I equals 2 plus 3I. So how could I go from here to that equation? Just change the plus to a minus? So I change this plus to a minus like that? Is that the same as what we have up here?
Oh, wait.
That ain't the same. That. My question is, how do we go from this equation right here to this one in pink? Notice the one in pink has negative 3 plus 4I minus the negative 5 plus I to equal the 2 plus 3I. So how do we go to that pink equation? Say again. Plus I minus 5. Okay, so you're like adding what again? Okay, now I want you to think about this. This is actually really, really, really close. But what do I get when I do negative 5 plus, oh, then notice if I do that on the left-hand side, I have to add that to the right-hand side, don't I? What's that called again? Property of equality. Now, I was called kind of Davian. You started to say an I word. What was that word you almost said? Inverses. Am I using an inverse right now?
Yes.
Am I?
Wait.
Those are the same. That's not inverses.
Oh, no. My bad.
What would I need to do to make them inverses? Oh, I need to subtract, don't I? And what's any number minus itself?
8 times 9.
So inverses and properties of equality, do they hold with the imaginary numbers? That's all I want you to see there. So I would make those two quick notes, right? You can distribute with imaginary numbers, and inverses with properties of equality also hold in the complex number system. So one thing I would point out, Landon, what you were originally saying is you said plus 5 and minus I. Well, that's the same as subtracting a negative and subtracting a positive. Same exact thing.
Can you repeat that?
Which part?
The,
What you want us to write down?
Inverses?
yeah.
Up here, I would note that distribution works with the complex numbers, and inverses with properties of equality work with complex numbers.
Can you like write that down on the board?
No.
One more time.
What was that?
Inverses
Okay.
with properties of equality
Inverse.
work with complex numbers. Guys, y'all, you've been doing inverses with properties of equality for a few weeks now, right? Inverses with properties of equality just work with complex numbers. That's it. Y'all making that way too hard. Kennedy, you good? Falling asleep on me over there? Trying to fall asleep on me? Oof, we gotta get moving last little bit. We already tackled 7 and 8. Alright, this is all I want you to work on now. I'm skipping ahead to page 104 after you get those notes, because we actually kind of jumped ahead and did a little bit. On page 104, I want you to perform each operation at your vertical surfaces and show your work, and then we're going to discuss. That's okay. I'm asking for predictions.
Center of the room, guys, center of the room.
Okay.
Go on.
So, first things first, hey guys, I need y'all to be careful about this. One, what property did I say does hold up with imaginary numbers? So I can't, let me rephrase this. Real numbers go with real numbers, imaginary with imaginary when we're doing what operation? With adding and subtracting, okay? But what property does hold with imaginary numbers or complex numbers? What? Well, what with that multiplication starts with D? Distribution, right? You always distribute, right? So one way to see this right here, just to make things easier, is this is 3 plus 2i minus 1 plus 6i. I think a lot of us got there. Just want to emphasize that. Do note, if I want to show clear evidence that you understand what's going on, I just rewrote it so that my reals are with my reals, my imaginary with my imaginary, and then I get my final answer of 2 plus 8i. Same thing here. This group, right, show the things that go together. I would probably just rewrite it like this. Notice I got my reals, my imaginary with my imaginary. Okay? Now, what I want to really actually emphasize is C and D. So with C, what property do I need to use? Distributive property, right? Multiply it out. And so 5i times 3, notice I can do that. And the reason why is this. If I have 3 times 5i, what does that mean I have in all reality? I have 5i how many times? 3 times, right? So I can distribute with complex numbers. You can distribute a real to a complex number, an imaginary number, all right? You just can't add and subtract real and imaginary. You have to leave those two different terms. But we get 15i, and we need to be careful. What's 5i times a negative 2i? Negative 10. Notice I am doing I times I, which is I squared. And so some groups left it like this, whereas this group rewrote it as 15i plus 10. Who is correct?
And both correct.
So both are mathematically correct, but which one do you think we want it written as? You want to rewrite it with a real number piece if you can. And so remember, I is equal to the square root of negative 1 because I squared was what? Was negative 1, right? Like that was actually the defining piece. We defined I such that I squared is negative 1. So when I have 15i minus 10i squared, how am I going to rewrite that I squared? I squared is, and a negative times a negative is. So there's only one thing I would change about this. Don't have to, but I definitely would. Why'd I write it as 10 plus 15i? I want my real, then I want my imaginary. I want real, then I want imaginary. Now, before we talk about D, I need us to hear and pay attention to this. You have not and will never hear me say FOIL in this classroom. FOIL is something that only works in one specific case. And I know some teachers still teach it. Mr. Javi, in your math classes and all your stuff at UA, what have you been taught about FOIL?
Is that it only works for 2 terms and 2 terms?
It's only 2 terms by 2 terms, and that's it. I've heard some teachers say FOIL is the F word in their classroom, as in like the dirty curse word. We don't use it. Here's why. Guys, if I did first, outside, inside, and last, what did I completely miss? I completely missed that minus 4x. If you do FOIL, that only works with 2 terms times 2 terms, which is why you never hear me talk about it, because it doesn't always work. However, if you distribute, if you use an area model, either one, will you miss any of those terms? No. It's distributing. I don't understand legitimately why teachers still teach it. That's their prerogative. I just don't get it. Distributing always works. The area model always works. So you will always hear me say distribute or use the area model. I don't use FOIL. That's why. And then I have my like terms. All that to come back here to 5 plus 3i times 2 minus 3i. Doesn't that kind of look like a binomial, 2 terms times 2 terms? So how do I multiply them? Distribute or area model. What's 2 times 5? What's 2 times 3i? Negative 3i times 5. Negative 15i. negative 3i times positive 3i. Negative 9i squared. We need to be careful about that. And so I'm going to just go ahead and rewrite this with my like term. Well, I see my like terms right here for sure. What is 6 minus 15, or 6i minus 15i? Negative 9i, cool. Now, we need to look again. How can I rewrite this right here? Plus 9. If you're confused where Landon's getting that from, remember I squared is what? Negative 1. So negative times negative is a positive, and now that would be the correct term here. So, for the most part, I think A and B were really strong. I think C and D is where you probably need to write some notes to yourself about distribution and making sure that with our complex numbers and multiplying, what property do we make sure we use? What property do we use? Distribution. Again, I did not make check your understanding questions, but you know what there's a ton of on Mathia? Complex numbers. So those are your check your understanding questions for this unit. Mathia has your complex numbers. I think Elizabeth, you even started working on that last week. Like you got to that point with the imaginary numbers and like you saw a lot of this. I think it has graphing, but I know for sure it has adding, subtracting, multiplying. I think it even has some sorting of those numbers. Please do your Mathia. Take this time to add whatever notes you need to about these numbers.